Hey guys, I'm going to go over the midterm practice test that we took in class this week. I've already jotted down a lot of the answers and I will post the PDF of this online. So I will just kind of run through this relatively quickly. For questions 1 and 2 for the position and velocity graphs, when you are answering it on the test, you should have it laid out with both the times and the position or the velocity. So for instance, for segment 1, you would say seconds 1 to 2, then seconds 2 to 3, seconds 3 to 4. I didn't lay out the various times. I just kind of labeled where what the answers were, just because there's not much space and just to kind of run through this a little bit more quickly. So in this first segment here, seconds 1 to 2, what we need to remember is that negative numbers here means that you're behind the motion sensor. So the very first thing that I would do when you're analyzing any of these graphs is, as you can see here, draw a line where 0 is and then label what it means to be positive and negative. That's probably the most confusing part about these graphs, and if you've got that figured out, meaning if you know that you are dealing with a position graph, and if it's positive and you're in front and negative and you're behind, then it's a lot easier to interpret what these different lines mean. So this means you're standing 1 meter behind. Then you move to 2 meters from 1 meter. In the next segment, you stay at 2 meters behind. You should actually write in behind. From seconds 4 to 5, you move back to on top, quote unquote, of the motion sensor, right? Seconds 5 to 6, you stand still right on top of the motion sensor. And then seconds 6 to 11, you go from 0 meters to 6 meters in front of the motion sensor. Seconds 11 to 12, you stay at 6 meters. 12 to 13, you go from 5 meters to 4 meters, still in front. And then in the last segment here, you stay at 4 meters. So remember, these do not, when you're doing this on the test, they do not need to be in full sentences. They can be in note form. So for instance, you could say seconds 1 to 2, and it's stand 1m behind, right? Keep it short and simple. Keep it in note form. You've got all the information. You've got your time, you've got whatever the action is, and you've got the distance. So we're going to move on to velocity here. Very first step, label what this graph means. So, make the x-axis even darker, even more obvious, and then label that if you are in positive numbers, that means you're moving away, and if you're in negative numbers, that means you're moving towards. So in these cases, when we're talking about velocity, negative numbers doesn't mean smaller. So it doesn't mean that you're getting slower and slower. You can't get slower than 0 meters per second. So if you're getting more and more negative, you're actually getting faster and faster. That negative sign just means it's an indicator, it's a symbol that tells you that you are moving towards. So really, these should almost say +1, +2, to remind us that that plus sign is just an indicator, that symbol of moving away. So the bigger the numbers get in either direction, the faster you are going. So I've labeled your answers here. This flat line at -1 means you're moving a constant velocity towards the motion sensor at -1 meters per second. This slanted line going from -1 to -2 tells you that you are still going towards, because you're in the negatives. You're speeding up because it's getting more negative, and you're speeding up from -1 to -2 meters per second. Flat line again tells you it's a constant velocity of -2, and you're still going towards. As this line goes back towards 0, that means you're slowing down. Slowing down from -2 to 0 meters per second, like it says right here. And that should be an arrow there. Since it's still negative, you're still going towards. This flat line right on the 0 means you're not moving. You're standing still. That would be all you'd need to say. From seconds 6 to 11, those numbers are getting bigger. You're going from 0 meters per second to 5 meters per second. So you're moving away, speeding up, and there's your speed. Flat line at 5, constant velocity, 5 meters per second, away. Decreasing line, you're moving away, slowing down, 5 to 4 meters per second. Flat line, constant, away, 4 meters per second. So once again, note form is okay. You should still include your seconds, so for seconds 1 to 2, and then tell me what you're doing. But it's okay to write it not in a complete sentence and do it in totally note form. So, again, kind of highlight that x-axis. If you're in positive numbers, you're speeding up. If you're in negative numbers, you're slowing down. The acceleration graph does not tell us the direction. It just tells us if we're speeding up or down, because it's already using the positive and negative numbers just to indicate faster or slower. So remember, anytime you're in the negatives, you're slowing down. Whether the line's going up or down tells you by what rate you are slowing down, meaning are those jumps getting bigger or getting smaller. So in this first one, you're slowing down at a negative rate of -1 meters, or at a constant rate of -1 meters per second squared. Here, that line is getting more negative, so you're slowing down more. Or another way of saying that is slowing down faster. This flat line is you're going to continue slowing down at a constant rate. That line is going closer and closer to 0, so you're actually slowing down slower. There is less deceleration, right? Rather than slowing down by jumps of 2, eventually you're slowing down by jumps of 1, then jumps of 0. So not slowing down at all anymore, and in fact, for this segment, traveling a constant speed. So how negative these numbers are really means how quickly and how quickly you're slowing down. So if you were on a bike or in a car, how hard you press on the brakes will determine how quickly you slow down. So tapping the brakes would be like slowing down at -1. Slamming on the brakes would be like slowing down at -10, where you're slowing down at a much faster rate. Here, your rate of acceleration is getting faster every second. So you're not only speeding up or accelerating, but you're doing so more quickly or faster every single second. Flat line tells you constant acceleration. Decreasing line tells you you're still speeding up because it's in the positives, but you're just doing so more slowly. So you're still getting faster, but the rate at which you're getting faster is a little bit lower. And here, another flat line, constant acceleration. Remember that if you are labeling an acceleration graph, you don't need to talk about the various times or the various rates of acceleration. Just tell me what the lines themselves mean. So just label them so that it is clear that you know that I can tell that you know that an increasing line means speeding up and doing so faster, and a decreasing line means you're still speeding up but doing so slower. So something like this, what I have here, would be totally fine. For number 4, please label where on the graph you might find these items, if it is a velocity graph. So when we are looking for A, when you are farthest from the motion sensor, since it's a velocity graph, all of your positive numbers means away. So when you are farthest, we are looking for when you spend the most time moving away from the motion sensor. So that would occur right here, right? Moving away, 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 away. That's when you've moved away for the farthest amount of time. Therefore, you are the farthest. When you're looking for closest, you're looking for where you spend the most time moving towards. All of your negative numbers are towards. So away, towards, and that's right here where you would cross into 0 is where you stop going towards. So that's where you could label B. When you are traveling a constant velocity, that would be any flat line. So that would be here, 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 and here. That is when your velocity is constant. You are going to accelerate anytime your velocity changes, so that would be anytime the line goes up or down. So here you are decelerating, accelerating, decelerating, accelerating, decelerating. So anytime the line goes up or down, you would be accelerating. So I'm going to run through these pretty quickly as well. If we've got our 100-kilogram rocket, right? Here's the fire. There's your rocket. It's 100 kilograms, so F of G is going to be 100 kg times 10, which gives you 1,000 newtons of downward force. And it's got a total force of 20,000 newtons. So we subtract these two because you need to spend 1,000 newtons overcoming gravity. You're left over with 19,000 newtons of force to accelerate this rocket. Now this rocket has a mass of 100 kilograms. So you divide those, cross out a 0, cross out a 0, you're left with 190 meters per second squared. If you're confused about the details of rocket problems, I have 2 different rocket problem videos, so go and watch that video which will explain the same process in much more detail and much more slowly. So number 6 is just working number 5 backwards. Essentially, if you want to accelerate it at 20 meters per second squared, you also need to accelerate it fast enough to overcome the rate of acceleration due to gravity. So that would be another 10 meters per second squared. So that's why I multiplied the mass by 30, which is 20 plus 10, giving us 900, I'm going to write that more neatly, 900 newtons of total force necessary. Once again, if this problem is confusing to you, go watch the rocket problem video. It explains it in greater detail. For both of these questions, 7 and 8, there's the video about what is weight. If it's a 12 kilogram object and it's on Earth, you multiply it by the rate of acceleration due to gravity on Earth, which is 10. 10 times 12 is 120. If you're on Mars, the acceleration due to gravity is 4. So instead of multiplying it by 10, we multiply 12 by 4 and get 48 newtons. In number 9, you speed up from 0 to 20 in 5 seconds. So to find your acceleration, you take 20 divided by 5 and get 4 meters per second squared. That's your acceleration. How far? D equals 1/2 AT squared. So 1/2 of A, meaning 1/2 of 4, is 2 times your time squared, which is 10 squared. So if I write that out for you, D equals 1/2 times 4 times 10 squared, right? Which then simplifies to that, and you get 200 meters is what that answer is. Confused on that video, watch the acceleration. There's a couple different acceleration videos that you could watch. So we're going to skip number 10 just for a moment. Number 11, I think this was supposed to be a friction problem, but I wrote it so fast I forgot to add in what the force of friction was. So once again, here's our first speed, our second speed, and our time. So we subtract 10 minus 2, which would be 8, divided by 4, which gives us a rate of acceleration of 2 meters per second squared. Multiply that by the mass, and we get 20 newtons. If I had remembered to talk about the 2 newtons of friction, let's say, we would add those two numbers together to find what the total force necessary would be, which would be 22 newtons, for instance, right? I'm making that up. But 20 was the answer to number 11. So number 10 also has a video about it. It's slightly different wording and it's slightly different numbers, but it is called Calculating Speed from a Data Table. The important thing to remember here is that with Mr. Truck or Maya and her drive, we also did one on Susie's drive to school, these distances and these times are not distances covered or time elapsed, but they are recording at what time they pass a mile marker, or in this case a meter marker. So it doesn't mean that Mr. Truck has driven 10 meters in 5 seconds. It means that when he passes the 10 meter mark, the time is 5 seconds. So what we need to do is figure out, actually, he drove from the 10 meter mark to the 20 meter mark, driving 10 meters, in 5 seconds. Here he drove 1 meter in 5 seconds, 19 meters in 5 seconds, and 5 meters in 5 seconds. So, answering this question, where did he drive the fastest? You look for the biggest distance, 19 meters. That's from time 15 to 20. How fast does he drive in his slowest time? That would be where he goes the least distance, 1 meter in 5 seconds. His average speed from seconds 5 to 10, so that's going to be 10 meters in 5 seconds, right? Because that's looking at it right here. His average speed for the whole trip, we can't add up 10, 20, and 21. He didn't drive those. He drove from 10 to 45. So that's why we take 45 minus 10 and 25 minus 5. So in each of these cases, if you were confused about the process in solving these, I know I went through them fast, go and find the video that talks about each individual problem, because there's a video for every single one of these problems up there. Send me an email if you've got any questions.